Okay, the intermediate value theorem. Before you go through this PowerPoint, be sure that you've looked at the tutorial at calculus-help.com. It's lesson number 6. Okay, the intermediate value theorem is used in calculus to prove other theorems. So I'm going to introduce it to you this year, and we're going to use it to find roots, real roots for our polynomials, and I'll show you how it works in a second. But let's take a look at the theorem itself. Okay, there's what the theorem says. If you have a polynomial p of x, now it can be any smooth continuous function p of x on a closed interval ab, for any value c between p of a and p of b, there is at least one x value on that closed interval ab such that p of x equals c. Alright, so here it is. There's a and there's b, our closed interval. And we're going to find p of a and p of b. Okay, the intermediate value theorem says that if you find any y value between p of a and p of b, that x value is guaranteed to lie between a and b. And you're guaranteed to have at least one. You could have more, but at least one. That's the theorem. Now, it's not true that for any x value between a and b that there's at least one y value between p of a and p of b, and I'll show you here. Okay, so there's our closed interval ab, and there is c. It's located between a and b, and let's find our y values. You can see that p of c does not lie between p of a and p of b, so it only works the other way. So make sure you understand that. Okay, now how are we going to use this? Well, if we find a closed interval, say a and b, and we know that one of our values, such as in this graph, p of a is positive. P of a is, let's go back and get my pen. Sorry about that. P of a is positive, so it's right here. It's a positive value. And P of b is negative. P of b is negative. Well, 0 lies between a positive and a negative value. So here's when P of x equals 0. So if we're doing our charts and we find an output that's positive and then we find an output that's negative, we might check an x value that's between those two outputs to check to see if there is indeed a 0. Now this will work if there's rational roots. If there's irrational roots, then we're not going to be able to use the theorem. But that's how we're going to use it. We have a positive and we have a negative, so we know that there's at least one 0 on the closed interval AB. Alright, and here's the example. Okay, let's start by writing our list of possible rational roots, last over first. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. Okay, now I'm going to use the synthetic division to test these roots. So I put down my coefficients, 1, negative 4, negative 11, 30. Okay, I'm going to try 1 first. So if I try 1, I'm going to use the compact chart. Bring down the 1, add it, that's negative 3, add it, it's negative 14, add it, and it's 16. This is a positive y value. Okay, now I'm going to try 3. That doesn't work, but I know that f of 1 is equal to 16. Now I'm going to try 3. It's negative 1. It's negative 14. And then that would be negative 42, so that's negative 12. So here's a negative y value. so I plugged in 1 and I get 16, which is positive. I plugged in 3 and I get negative 12, which is negative. So I know that there is some x value between 1 and 3 such that its y value is 0. So let's try 2. So if we tried 2, that didn't work. So if I try, we bring down the 1, that's negative 2, that's negative 4, that's negative 15, negative 15, 30, and that's 0. So yahoo, we found an x-intercept, a real root. So then we've got a quadratic and we could finish factoring it. That's how it works. Now I knew what the answer was, so I used the 1 and the 3. But sometimes if you're having trouble, you can watch your y values and see if one's positive, one's negative. You can try an x between that and hope that you find a 0. Now you can do all of it without using this theorem. I just wanted to introduce the theorem to you because it is used in higher math. Alright, I probably have a graph of it, and there it is. So let's review what we found on the previous page. We found that when x is equal to 1, p of 1 is equal to 16, and then we found when x is equal to 3, p of 3 or f of 3 is equal to negative 12. Then in between 16 and negative 12, there's a 0, such that that x value lies between 1 and 3, and the x value is 2. It has to be rational though, remember. And that's it.